So we're going to talk a little bit about stress magnitudes at depth. And these are just, so you'll see these in Zobac's book. These are just qualitative sort of diagrams that give you that show you what the relationship is between the principal stresses as defined by the Andersonian classification scheme. So remember, in a normal faulting regime, what's the greatest principal stress? We learned it last time. No, vertical, right? Remember, if you can remember I told you you remember normal, strike, slip, reverse. The vertical is on the diagonal of that table, right, that I drew. So you can sort of draw the table in your head. So normal, the vertical. Also, if you just look at the plot, I had it written there. Okay. But anyway, so these sort of constrain the relationship between the principal stresses and the pore pressure. And you can see that, so in a normal faulting regime, the vertical stress is here. And the vertical stress, we can estimate relatively well how? I mean, that's more than an estimation. That's really a computation, right? So we can integrate the density logs, or we also have some rules of thumb, right? How does vertical stress increase with depth in terms of PSI per foot? 1 PSI per foot. Right? It's easy, 1 PSI per foot. So essentially this line is drawn just like that, 1 PSI per foot. And since the vertical stress is the maximum one, we know all the other ones are going to be on the other side of it. Okay? But we also know that the minimum horizontal principal stress, the minimum principal stress, in any case, has to be greater than the pore pressure. Otherwise, you get hydraulic fracturing. So if we draw a line for the pore pressure, and we haven't talked about exactly how to come up with that. I'll talk about it in just a minute. But essentially, you can also estimate that in terms of hydrostatic. What I mean by I say hydrostatic is that vertical line is just as if it were a column of water. Right? So the pressure, if it was just a solid column of water all the way up. Right? And it turns out that that's about 0.44 psi per foot. Right? So that's two lines that we can that give us the sort of upper bound and lower bound. And then we just order our principal stresses in between, SH max and SH min. These kind of long lines, the pluses would be representative of SH min, the dot would be SH max, and just understand that it could sort of move anywhere along this line. And the distance between the two is governed by the strength of the rock. Right? So we haven't really talked about that yet, but again, we'll see very soon that the difference in principal stresses sort of is a bound on the strength of the rock, because if those two guys are too far apart, then you'll exceed the compressive strength of the rock and actually fail it in that way. So that's why you see, but they can move along this bound a little bit. Okay, so this would be for the hydrostatic case. For a case of overpressure, so if hydrostatic is if hydrostatic is defined as if it were just the pore pressure, if it were just a column of water, then a scenario of overpressure is just defined as anything more than that. Okay, anything more than that, but approaching the vertical stress. So the pore pressure can also never be greater than the vertical stress. I mean, if it did, then the Earth would just be floating, right? I mean, the material would just float on top of water, right? So while in an overpressure scenario, it can approach the vertical stress, it can never exceed it. So as it approaches the vertical stress, based on the other rules we have, we can't hydraulically fracture the rock, and of course SH min is less than SH max, then it squeezes these down. Right? So this is just a qualitative look at the relationship between the stresses. So same thing in the strike-slip regime. So, essentially all we're doing is we're drawing the same two lines, the pore pressure at hydrostatic and the vertical stress, because those are the two we can estimate relatively well without any other knowledge. And then in a strike-slip regime, we know that that the vertical stress is the middle, right? It's between the other two. And so then SH max would be on the outside there, and SH min would be in the middle, and the distance between them is still governed by the strength of the rock. Okay? And the same thing, there's really no change here. When you go to an overpressure scenario, it just squeezes those bounds down, because the pore pressure can never exceed the vertical stress. Reverse faulting. In a reverse faulting regime, what's the vertical stress in terms of the other two? It's the smallest, right? It's the least, right? So we still draw it, but now the other two are to the right side, okay? And you still see some effect when you go into an overpressure scenario, that the distance between these two will be squeezed down, and that has to do with the effect that the pore pressure plays. Okay, and we'll see that when we start actually talking about the constituent models for these guys. You can actually use the pore pressure in some cases as either a stabilizing effect in terms of wellbore stability. We can go to a little bit of an overpressure scenario to allow the principal stresses to maintain some distance from one another, so that the rock won't fail. We'll see that soon. So I think we've already talked a little bit about this, but in terms of a couple of them, how we measure stress in the earth. But really what this is a preview of things to come in terms of what we're going to talk about in more detail. The first one we've already talked about, though. So the vertical stress we can get from the integration of density logs, or just flat out estimating 1 psi per foot. S3, which is SH min for normal faulting and strike-slip faulting, is obtained from mini-fracs and leack-off tests. So we'll talk about these later. These are essentially little hydraulic fractures that are done on purpose in the course of drilling usually. Occasionally you'll stop and you'll perform one of these tests, and then you'll look at the pressure, the bottom hole pressure profile, and you can infer some information from the bottom hole pressure about when you create a hydraulic fracture and when it closes. And then from that you can determine or get a relatively good estimate of what the minimum horizontal principal stress, or what S3 is, okay? And so we'll talk more about that. We'll actually look at some bottom hole pressure logs from one of these tests, and I'll show you, and you'll even have some questions on how to exactly choose what the appropriate S3 or SH min is, okay? So the pore pressure can be measured directly or estimated from geophysical logs. So when we're drilling, we have tools that help us measure bottom hole pressure and everything. So that's how we can measure the pore pressure. You can also infer some information from the seismic data. So then if we know SH min, from a mini-frac, and if we know the vertical stress from integration of density logs, then we can usually bound SH max with the frictional strength of the crust, okay? So this has to do with, again, the strength of the rock is proportional, or one failure model tells us that the strength of the rock is proportional to the difference in principal stresses, okay? But in reality, that would be true if you had a completely intact rock you're testing in the laboratory. But in reality, most of the earth is already fractured, okay? So there's lots of little faults and fractures in the earth, And it turns out that it's actually the friction on those fractures that more or less governs what the other principal stress is, okay? Because those fractures will slip. Before the fractures will slip before you can actually create new fractures in many cases. Okay, so with that information, we can bound SH max, and we'll talk about that. And then, the orientation of principal stresses. So we talked about we need 4 things to completely characterize the stress, right? 3 of those are magnitudes, and those encompass the first 4 bullet points of how we come up with those. And the other thing is we need the direction of one of the horizontal principal stresses, okay? And so we can get that from wellbore observations. Later we'll look at wellbores, and wellbores almost ubiquitously always have some breakouts, some region where the rock is beginning to fail. That doesn't mean that you have an unstable wellbore. Many times, that can lead to wellbore instability. If you have lots of breakouts such that essentially the wellbore collapses on itself, that would be a bad thing. But in terms of, you can have small breakouts along the wellbore, and we can use our knowledge of the stress state around the wellbore to help us determine what direction those breakouts occur at. They always occur in pairs. Well, they commonly occur in pairs along the side of the wellbore, and it turns out we'll see that corresponds to one of the principal stress directions. And so we can use that information to help us determine it. Also from the mini-frac tests and other things, if we're actually doing hydraulic fractures, we can use that information to understand what the directions are, principal stresses. Also, just the geology and earthquake focal mechanisms can also be helpful. In where the earthquake data is a little bit, it can be helpful in areas where you have very large differences in principal stresses, but in areas where the principal stresses are small, the difference in principal stresses are small, it can be difficult to determine directions that way. And that's actually the case in California. We have a ton of earthquake data in California, but it's not that reliable in terms of the stress directions. So, see if I can get this to work. Yeah, okay. So we have these stress maps. I provide a reference there to this paper, but basically this is a compilation of stress data that's taken from numerous sources, including essentially all of those I just mentioned: breakouts, hydraulic fractures, mini-fracture tests, other local measurements, earthquake focal point. And so the colors represent the sort of types of measurements you see, and the dots are really just sort of where all these will occur, and the lines indicate the direction of maximum horizontal principal stress. Yeah. And what?
Is there a correlation between this and the MATLAB,
Not really. No. Yeah.
It just looks
Yeah. The homework was actual GPS sensors measuring the motion of the tectonic, actually measuring the motion of the plates, right? Here these measurements were taken in the ground to indicate the state of stress. Okay. So I guess the point of this is that if you had a geomechanical problem that you need to solve related to wellbore stability or other things, and you had zero data about the state of stress on the earth there, you could maybe go to one of these maps and look for some nearby, because if you don't know anything, you have to be an engineer, right? You have to try to do something. And so you can look for some nearby measurements and sort of use that as the best estimate of the state of stress in the area. And so, but these are where we have measurements, and they're continually being updated. You can see there's some consistency in some regions, right? So if you're in Canada there, you could say with some confidence that the principal stress is to the north. Maximum direction of SH max is in the northeast direction. So, In some cases, you get lucky.